So continuing with from where we left, what is an electron volt? An electron volt is a very small unit of energy and it is represented by EV, which is equals to 1.6 exponent minus 19 joules. 1 electron volt can be defined as the amount of energy gained or lost by an electron because it transfers a potential difference of a 1 volt. So derivation is delta U is equals to Q del V. Delta U becomes delta KE, which is the change in kinetic energy, and it equates delta U. Delta KE is equals to K delta V, which is K is electron and delta V is 1 volt. So delta KE becomes Q del V, and we place the numerical value of that, which we get 1.6 exponent minus 19 CV. CV is equals to joule, and delta KE is equals to 1.6 exponent minus 19 joules. For converting joule to electron volt, we divide it by 1.6, and for converting electron volt to joule, we multiply it by 1.6 exponent 19. Electric and gravitational forces comparison was there in the book, but it's not in the SLOs, so you can have a look in the book as well. Millikan oil drop method. Its purpose was in 1909, R. A. Millikan, a scientist, devised a technique to find charge on electron, and he knew that the mass of electron wasn't known. So he constructed an experimental method. Number 1, he used an observation chamber C, two parallel plates P and P prime. Two upper plates had a small hole H, window W1 for light source, window W2 to connect from DC source, and atomizer used for spraying oil droplets in the chamber, a microscope to observe the path of the droplet motion. Let's see the working of it. The tiny droplets are sprayed into the chamber through the small nozzle of the atomizer. First, the tiny droplets are sprayed into the chamber like this, and the droplets get negatively charged due to the friction between the walls of atomizer and oil drops. They get a negative charge. Some of these drops pass through the hole, and when they pass through the hole in the upper plate, a potential difference is applied between the plates to produce the electric force. A potential difference is applied between the two plates. Now the electric field between the plates P and P prime is adjusted in such a way that the electric force becomes equal to the gravitational force on the drop, and in this case the oil droplets become suspended in the air. For the mathematical derivation, charge on the oil drop, electric field becomes equated to gravitational field EQ. As we know, F is equals to EQ and Fg is equals to mg, so Q is equals to mg upon E, where E, as we know, is equals to V upon D. So we'll put the value over here, and now we'll arrange for Q, so it becomes Q is equals to mgd upon V, which is equation number 1. Mass of oil droplet is Fd is equals to Fg, where Fd is equals to 6 pi nr, 6 pi eta r Vt. Vt is the terminal velocity and Fg is mg. When we rearrange it for m, it becomes 6 pi nr, 6 pi eta r Vt upon g, where r is the radius of the droplet and Vt is the displacement s upon t. This becomes our equation number 2. Moving further down, radius of the droplet, as it is a sphere, we know sphere, so rho is equals to m upon v, and m will become rho into v. M is 4 pi 3 pi r cube. Volume comes here as a sphere is there, and rho comes as it is. So m is equals to 4 upon 3 pi r cube rho. M is equals to 6 pi eta r Vt upon g, and we'll compare these two equations. So we'll find out the radius value. First we'll find the r square, and then we'll under root both sides, so we'll get under root 9 eta Vt upon 2 rho g, which is equation number 3. Conclusion is that Millikan can calculate the charge on all droplets was an integral multiple of 1.6 exponent minus 19 coulomb. Capacitor. A capacitor is a device that can store charges or energy. Parallel plate capacitor consists of two conductor plates near one another separated by vacuum or any other insulator called the dielectric. Its symbol is simple. Draw a straight line and two lines like this and one more line like this. Mathematical form is Q is directly proportional to V, so constant comes over here, C, which is known as a capacitance, and capacitance is the ability to store charge. C is equals to Q upon V. As the plates are shown over here, it is the distance d between the plates. Amount of charge on a plate necessary to raise the potential of that plate by 1 volt, which is C is equals to Q. Factors are geometry of the plates, and second is the medium between them. Unit is C is equals to Q upon V, which is equals to 1 coulomb upon 1 volt, and this is equals to 1 farad. The capacitance of a capacitor is 1 farad if a charge of 1 coulomb given to one of the plates of a parallel plate capacitor produces a potential difference of 1 volt between them. So for example, if C is unknown, V is 3 volts and Q is 9 coulombs, so Q upon V becomes 9 upon 3, which is 3 farad. And if we increase exponentially, like 3 becomes 6 and 9 becomes 2, still the ratio remains the same. Capacitance of a parallel plate capacitor PPC, as we know, C vacuum, capacitance in the vacuum is equal to Q upon V, so sigma is equals to Q upon A, which is C upon MC square. E is equals to sigma upon epsilon naught, which is the charge density, so E becomes Q upon A epsilon naught, which is equation number 2, and this is equation number 1. As we also know that E is equals to V upon D, so we'll compare 2 and 3. V upon D is equals to Q upon A epsilon naught. Q upon V is equals to A epsilon naught upon D. So C vacuum becomes A epsilon naught upon D. In the presence of the medium dielectric, C medium is equals to A epsilon naught upon D, and relative permittivity is also included, which is greater than 1. C med is equals to C vac into ER, and C medium is always greater than capacitance of the vacuum. Looking at the factors that affect the capacitance is number 1, area of plates. C increases as the area of plates increases. Distance between the plates. C increases with the decrease in the distance. Medium or dielectric presence of an insulating material medium increases C with a factor of ER. If C increases, V decreases. C is equals to A epsilon naught R, which is relative permittivity, epsilon R, and upon D. Relative permittivity is the ratio of two capacitance, which is capacitance of medium and capacitance in vacuum. What is electric polarization of a dielectric? Dielectric is that consists of atoms or molecules which are electrically neutral, or on average they can contain equal amount of positive and negative charge. In the absence of the electric field, distribution of these charges in the atoms and molecules is such that the center of the positive charge coincides with the center of the negative charge. While in the presence of the electric field, when the molecules are subjected to an electric field, the negative charges are attracted towards the positively charged plate, and positive charges are towards the negatively charged plates. So, when the electrons and the nuclei undergo slight displacement in an electric field, so as a result, the displacement in the electric field has been made. As a result of this displacement, center of the positive and negative charges no longer coincides with each other, and one end shows a negative and other end shows a positive charge, but atoms are still as a whole neutral. What is a dipole? Dipole has two equal and opposite charges which is separated by a small distance, which are said to constitute a dipole. Polarization is the phenomena of making a molecule into a dipole is called polarization. The effects of polarization are effect of charge Q remains same, effect on electrical intensity E decreases, opposite internal electricity are developed, so it in turn decreases it. Effect on the potential difference is that potential V decreases, so V decreases, E also decreases, Effect on capacitor is a capacitance increases, C increases, V decreases. Effect on the charge density, sigma also decreases as they are directly proportional, energy decreases, so sigma also decreases. Calculating the energy stored in a capacitor device used to store energy. Alternatively, it is possible to think of a capacitor as a device for storing electrical energy. Charges on plates possesses electrical potential energy. So this energy rises because work is done to deposit the charges on the plates, and this is due to the fact that each small increment of a charge being deposited during the charging process has an effect. The potential difference between the plates increases and a large amount of work is done needed to bring up the next increment of the charge. So the mathematical derivation of the energy stored by a capacitor can be done through electric potential difference is equal to charge into potential difference is equal to Q into average potential difference, which is 0 plus V upon 2. Potential energy becomes half QV. Q is, as we know, is equal to CV, so potential energy becomes half CV into V, which becomes half CV square. Energy in the form of electric field, V is equals to ED, C med, V as we know is equals to A epsilon naught, epsilon R upon D. So potential energy becomes 1 upon 2 A epsilon naught, epsilon R upon D into ED square. Opening the equation, we cancel out D with D square, and the rest of all comes in the potential energy formula. Half E square epsilon naught epsilon R AD. Energy density is the energy stored per unit volume, so we'll divide the calculated energy with the volume. As we know, A into D is also volume, so volume cuts with the volume, and we are remain with this factor, which is half E square epsilon naught epsilon R. So the last topic is charging of a capacitor. Many electric circuit consist of both capacitor and resistor. Such as a circuit is called RC circuit. Capacitor is not charged immediately, charged rapidly at start, but charging plate slows down gradually. Yes, first it's charged at a very high pace, but as the charges accumulate, it slows down the charging, and as time comes when the charging becomes zero or no more charge can be taken place by the capacitor. Time constant, time required by the capacitor to deposit 0.63 times or 63%. The equilibrium change Q0, 63% is 63 upon 100, which is 0.63. Charging time depends on the capacitance and the resistance. Hence the time constant is equal to the product of the capacitance and resistance of the circuit, which is equals to R into C. Small value of RC is rapid charging, and large value of RC means slow charging. Discharging of a capacitor do not charge immediately, discharge rapidly at start, but discharging rate also slows down very gradually. Time required by capacitor to discharge 0.63 times equilibrium charge Q0. Small RC value is rapid discharging, large RC value means slow discharging. These graphs for the previous ones I couldn't make, so only this one is over here. So at 63% it shows that its maximum charging is done, and this is the high charge, slow charge, T1 and T2. Next is current electricity chapter, which we'll do in the next session, inshallah. Till then, goodbye.